What happens when you make an engine that exceeds the speed capacity of Mach 10? Well, guess what? GE has this new advancement that may do the same thing. Down this brand new piece of mechanism, GE Aerospace has made a major breakthrough in jet engine technology that could revolutionize air travel. The company has developed a new engine capable of propelling aircraft at speeds exceeding Mach 10. This advancement brings the possibility of reusable hypersonic aircraft significantly closer to reality. According to a press release by GE, the company has recently conducted a groundbreaking test of what is believed to be the world's first hypersonic dual-mode ramjet rig, utilizing rotating detonation combustion within a supersonic flow stream. This innovative approach leverages the highly efficient rotating detonation combustion process within a dual-mode ramjet, also known as a dual-mode scramjet. While ramjets and scramjets are types of air-breathing jet engines that perform poorly at low speeds, they are capable of propelling aircraft or weapons at speeds ranging from Mach 3 to Mach 5 and beyond. This development is a significant step towards creating dual-mode ramjet-scramjets with much greater range. The potential impact could be even more substantial if this technology is combined with a rotation detonation, combustion-equipped turbofan engine, forming what is known as a turbine-based combined cycle compulsion system. GE has already been advancing this concept, having announced in June that it is collaborating with the Defense Advanced Research Projects Agency and the Air Force Research Lab on a rotation detonation combustion-equipped turbine-based combined cycle engine. According to GE Aerospace Military Engines CEO Amy Gowder, GE engineers are currently testing the transition mode at high supersonic speeds, focusing on the shift in thrust from the rotating detonation combustion-equipped turbine to the dual-mode ramjet and scramjet. This turbine-based combined cycle engine aims to integrate 4 different types of air-breathing jet engine technologies into one system, enabling an aircraft to take off and land using conventional turbofan power, while reaching hypersonic speeds using scramjet power during sustained flight. This concept has been suggested by at least 3 other companies previously. However, GE's design is unique in its use of rotating detonation combustion, which could significantly enhance the engine's compactness and efficiency compared to earlier attempts, potentially offering a more practical solution for hypersonic flight. A functioning turbine-based combined cycle engine has been considered the ultimate goal for reusable hypersonic aircraft, as the advanced propulsion systems used in today's hypersonic weapons cannot operate at the low speeds required for aircraft landing, making them single-use only. Why is GE's engine better than the existing models? Last November 2023, Atlanta-based aviation company Hermeus successfully demonstrated their turbine-based combined cycle Chimera engine's ability to transition from turbojet to ramjet power in a high-speed wind tunnel. Shortly after, Virginia-based Leidos secured a $334 million contract from the Air Force Research Lab to further develop a turbofan to scramjet design, aiming for even higher speeds. In 2017, Lockheed Martin, in collaboration with Aerojet Rocketdyne, announced the successful ground testing of a similar turbofan to dual-mode scramjet design under the highly secretive SR-72 program. While these designs are all promising, GE Aerospace's recent announcement might be the most promising combined-cycle hypersonic propulsion system to date. GE's design not only includes a turbofan to dual-mode scramjet, similar to the SR-72 and Mayhem projects, but also incorporates an additional advanced propulsion system, the rotating detonation engine. This addition could help address a significant technical challenge known in Lockheed Martin's SR-72 program, bridging the speed gap between the efficient range of turbofan power, which decreases above Mach 2, and scramjet power, which is less efficient below Mach 4. According to GE, their hypersonic dual-mode scramjet with rotating detonation combustion engine could achieve similar or greater speeds compared to other hypersonic engine designs. Additionally, it could significantly improve fuel efficiency and range, potentially resulting in a smaller and lighter package overall. This program, which has been underway for about a year, has progressed quickly, partly due to GE's acquisition of hypersonic-focused Innoveering LLC last year. Innoveering brought significant expertise in developing high-speed inlet designs, crucial for the performance of any jet engine. In a dual-mode scramjet, the inlet geometry must be both precise and often adjustable to manage shockwaves in the airstream at varying flight speeds. GE now anticipates being able to demonstrate this advanced new engine system as early as this year, 2024. What is a rotating detonation engine? In its simplest form, a rotating detonation engine is a propulsion system that offers greater efficiency than traditional air-breathing jet engines thanks to a more effective means of ignition. In some ways, a rotating detonation engine is an extension of pulse detonation engines, which are in themselves an extension of pulse jets. While this lineage may seem confusing, walking through each of them as developmental steps may make it easier to wrap our heads around how these engines work. Pulse jet engines work by mixing air and fuel within a combustion chamber and then igniting the mixture to fire out of a nozzle in rapid pulses rather than under consistent combustion as you might find in other jet engines. In pulse jet engines, as in nearly all combustion engines, how the air-fuel mixture burns is known as deflagration. In simple terms, deflagration means heating a substance until it burns away rapidly, but at subsonic speeds. A pulse detonation engine operates similarly to a pulse jet, but uses detonation instead of deflagration. Detonation involves the air-fuel mixture burning at supersonic speeds, essentially causing an explosion. Dr. Chris Combs, a professor of hypersonic and aerospace engineering at the University of Texas San Antonio, explains that detonation can lead to higher efficiencies because the reaction occurs in a very short time and space. In a pulse detonation engine, after the air and fuel mix, they ignite, causing deflagration. However, a pressure wave compresses unburned fuel, triggering detonation, which produces more thrust from the same fuel amount. In pulse detonation engines, the air and fuel mixture ignites in pulses, like in a pulse jet. But the detonation method enables higher speeds, up to Mach 5. Detonation releases more energy than deflagration, making these engines more efficient by producing more thrust with less fuel. A rotating detonation engine advances this concept further. Instead of the detonation wave exiting the aircraft for propulsion, it travels within a circular channel inside the engine. Fuel and oxidizers enter through small holes and are ignited by the fast-moving detonation waves. Dr. Combs notes that it's common for 3 to 5 detonation waves to circle the chamber simultaneously. This engine produces continuous thrust, unlike the pulse thrust of a pulse detonation engine, while benefiting from the higher efficiency of detonation combustion found in a rotating detonation engine. This design offers significant power in a fuel-efficient package, which is why the Defense Advanced Research Projects Agency is developing it for its Gambit missile. GE Aerospace has integrated the rotating detonation combustion process into its dual-mode ramjet and is also working to incorporate it into turbofan technology. This could address 2 major challenges in hypersonic aircraft propulsion: transitioning from turbofan to scramjet power and reducing the weight of turbine-based combined cycle engines. Before exploring this further, let's briefly explain what a turbine-based combined cycle engine is. How do turbine-based combined cycle engines work? Companies like Hermeus and Leidos are developing hypersonic aircraft that integrate 2 types of air-breathing jet engines: low-speed engines like turbojets and turbofans, and high-speed engines like ramjets and scramjets. This combination addresses the challenge of managing airflow from a complete stop to high supersonic speeds. Turbojets and turbofans use a compressor fan to draw in and compress air, mix it with fuel, and ignite it for propulsion. These engines work efficiently from a standstill up to about Mach 2, but lose efficiency near Mach 3. The compressor becomes a hindrance to the high-speed airflow. Ramjets and scramjets, which lack compressors, can't function at low speeds but excel above Mach 3. They use the high-speed airflow and shock waves created by the inlet design to compress the air before ignition. Ramjets slow the air to subsonic speeds for ignition, making them effective at lower speeds but limiting their top speed to around Mach 6. Scramjets, maintaining supersonic airflow throughout, face ignition challenges but can potentially reach speeds of Mach 10 or higher. Dual-mode ramjets can operate as either a ramjet or a scramjet, adjusting the inlet geometry to create the necessary shock waves for each speed range. Combining a low-speed engine with a high-speed one results in a turbine-based combined cycle engine, which allows for takeoff, high-speed flight, and landing using the appropriate engine mode. 3 American efforts are currently focused on developing such engines. Hermes Chimera is a turbojet ramjet design with plans for a more advanced turbofan ramjet system called Chimera 2. Leidos, linked to the Air Force Research Lab's Mayhem program, is working on a turbofan-charged scramjet system. Lockheed Martin and Aerojet Rocketdyne reported success with a turbofan dual-mode scramjet engine in 2017, though details have since become secretive. GE Aerospace, though not initially a major player in hypersonic aircraft, has incorporated efficient rotating detonation combustion into their engine designs. This innovation could enable GE to quickly become a leader in the field, keeping up with the transitions. In 2013, Brad Leland of Lockheed Martin highlighted the challenge of transitioning from turbofan to scramjet power due to their differing efficient speed ranges, with turbofans effective up to Mach 2 and scramjets performing well at Mach 4 and above. GE's dual-mode ramjet, typically efficient above Mach 3, incorporates rotating detonation combustion to operate at lower speeds, bridging the gap between turbofan and dual-mode ramjet power. GE plans to extend this technology to high-powered turbofan engines, enabling higher speeds and greater efficiency. In 2020, GE patented a turbofan engine with a rotating detonation afterburner, enhancing airflow pressure, speed, and temperature while incorporating heat management features. This innovation could benefit non-hypersonic tactical aircraft by increasing top speeds and fuel efficiency, crucial for developing sixth-generation fighters. Using rotating detonation combustion in both turbofan and dual-mode ramjet engines offers significant advantages for hypersonic and tactical aircraft propulsion. Reducing the weight, a major challenge in developing a turbine-based combined cycle engine, is managing weight. Aircraft must carry multiple engine types, making one engine type redundant and adding weight. However, engines using rotating detonation combustion can address this issue by providing efficient thrust generation in a smaller, lighter package. This technology could also shorten engine length, reducing overall aircraft size and weight. More efficient engines reduce fuel consumption or extend range, which is crucial for long-distance missions like intelligence or precision strikes. For example, the SR-71 needed 80,000 pounds of fuel for 2,500 miles. Although predicting the exact fuel efficiency of GE's new engine is challenging, it's expected to be more efficient and capable of higher speed. Dr. Combs suggests that this technology could enable aircraft to exceed Mach 10, potentially reaching Mach 12. GE just became a heavy contender in the hypersonic aircraft scene. GE has made significant progress in just 12 months and plans to fully demonstrate their dual-mode ramjet with rotating detonation combustion next year. However, they have not provided a timeline for a turbine-based combined cycle engine that would integrate this ramjet with a similar rotating detonation-equipped turbofan. Developing such an engine will also require creating an airframe capable of handling the extreme conditions of hypersonic flight. This engine could potentially be part of other experimental projects, such as Lockheed Martin's SR-72 program, which is rumored to be changing. Alternatively, it could be used in a new aircraft design. Regardless of its final application, hypersonic aircraft are advancing rapidly, bringing us closer to their realization. That ends today's video. Leave a like, comment, and subscribe for more. See you next time.